This is Soumen from IIT Kanpur. I am a PMR fellow. So let's start from the stereochemistry, the basic concept and is the preliminary idea. So welcome to the stereochemistry and consider two of the compounds we produced while finding all the isomers of the C7H16. So one is the 2-methyl hexane and the 3-methyl hexane. Two isomers is possible. So first we take the one example of this 2-methyl-hexane. So here you can see two position containing the one methyl group and another butyl group is there 1, 2, 3, 4. So 4 carbon is attached to here. So this is if we present in such a way that methyl, butyl and hydrogen. Now you place a mirror image. Now you can see the identical of this molecule. Now if you rotate this one same, so the 2-methyl hexane is superimposable with its mirror images. Now coming to the another molecule, another isomer, this is the 3-methyl hexane. So in case of 3-methyl hexane, here the carbon center containing one the ethyl group and carbon center containing one ethyl group. Okay, and another arm is containing the methyl group, and the third one is the propyl group, and the fourth one is the hydrogen. So you can see if we place a mirror and the rotate it, now it will generate another new molecule. So consider two of the compounds we produced while so coming to the conclusion, you can say that the compounds that are not super impossible with their mirror image are called chiral molecule, or 3-methyl hexane is a chiral molecule. The compounds that are superimposable with their mirror image are called achiral. So 2-methyl hexane is an achiral molecule. An atom with 4 different substituents is also called a stereogenic center or stereo center. Okay. Now, if we consider the 3-methyl hexane as in the previous slide, I told you the 3-methyl hexane is a chiral molecule. Now, if it is the chiral molecule, can we come to know whether it is the enantiomer or not? So, what is enantiomer? I'll come to the definition later. So, in this slide, why it is enantiomer? Let's see if we place this mirror image in this molecule, then you can generate a new molecule, not molecule, not a new isomer. So one isomer where the methyl group is below and the another isomer methyl group is above. So this is the two isomers of the existing one molecule. So two isomers that are super impossible mirror images are called as a enantiomer. Now coming to the CIP system revise. So we know whether molecule contains one chiral center or not. Why it is so chiral? Because if the one carbon atom contains four different atoms or substituents, then we can say it is a chiral molecule. Then if it is chiral, then what will be the stereo center like R or S? R full form is the rector, S full form is the sinister. So you can come to conclusion by the CIP system that whether the molecule contains the R isomer or the S isomer. Now, there are certain principles, certain rules. So one is the highest priority, which is the highest containing molecule. Let's say, let's say this is the propyl group, one, and the second group is the ethyl group. The third group is the methyl, and the fourth one is the hydrogen. Now, there are two rules. One is the positive rule, and second one is the negative rule. If it is follows the positive rule, then the clockwise rotation, then it is a R, and the anti-clockwise rotation, this is the S. And if it is follows the the negative rule, then the clockwise rotation will give you the S, the anti-clockwise rotation give you the R. So let's say this is the molecule, the last below one, the left side one, S3 molecule. Why it is S? So propyl group here, this is the one, ET, this is the second, and the methyl is the third, and the hydrogen is the fourth. So it is the rotating in the anti-clockwise way. So now it is a S molecule. Now if you go to another isomer, that is the clockwise rotation, that is the R molecule. R molecule. Why? Because the 4 is the back. That means the positive rule. It is follows the positive rule. So if a molecule follows the positive rule and the clockwise rotation will give you the R molecule, and the anti-clockwise rotation it will give the S molecule. Okay, so now coming to the important part of the stereochemistry is the stereocenter. So what is stereocenter? The stereocenter is defined as an atom on which an interchange of any two atoms or groups result in a new stereoisomer. So when the new stereoisomer is an enantiomer, the stereocenter is called as a chiral center. But remember one thing, that whether the all stereocenters are not tetrahedral. Let's say for an example, this is the CH3 and OH group. Now if we interchange between two groups, OH and hydrogen, it will give the new stereocenter, new stereoisomer. So first and second are the enantiomer, non-superimposable mirror images. Hence, the stereocenters is a chiral center. The another stereo center is called as the CH3 and CH3 group is the same side, then it is the cis isomer. Now if we interchange between two groups, the CH3 and hydrogen, see this hydrogen goes above, the CH3 goes down. Now stereo center, new stereo center. 3 and 4 are not enantiomer, they are diastereomer. Hence, in that case, stereo center are not chiral center. All the stages, although also they are not tetrahedral. Okay, now the stereo centers, all the chiral centers are the stereo center. So we know that though if one molecule contain more than one chiral center, that may not be chiral molecule or maybe chiral molecule. It is possible. So I have taken one example. This is the mesotartaric acid, where the two COOH group is there and the OH group is the two OH group in the same side. Now if you pass a plane of symmetry, you can see the OH group is mirror image to each other and the COOH group also mirror image to each other. Although this 1 and 2 or the two carbons are chiral center, but still this molecule is the achiral. Okay. Now diastereomer. So what is diastereomer? Let's say if we take this 2 bromo, a 3 bromo butanol. So A and B, this is the stereo is A and B, this is the enantiomer to each other, because if you see, if you place a mirror image, it will give you the superimposable mirror image. So this is the enantiomer, and the C and D, it is also enantiomer to each other, but A and C as diastereomers, because they are not mirror image to each other. Stereoisomers that are not mirror image to each other, that is called as a diastereomer. So A and C are diastereomer to each other. D and D also diastereomer to each other. So this is the definition of the diastereomers. Okay, A and B are enantiomer, C and D are enantiomer, but they are each to each other. These two enantiomers are diastereomer to each other. Okay, now we come to the geometrical isomer. So what is geometrical isomer? In case of geometrical isomers, occur as a result of restricted rotation about a carbon-carbon bond. So this is also called cis-trans isomerism. So if we see here, the CH3 and CH3 both group are same in the same side. So that is why it is called as a cis isomer. And here the CH3 and CH3 in the trans isomer, anti to each other, not in the same side. So that is why it is a trans isomer. Even the below one also example, CH3 and CH3 above of the plane, both in the above plane. So that is why it is a cis isomer. And the CH3 and CH3 is the below to the plane to each other. That is why it is a trans isomer. Here they are saying that in the definition they are itself they are saying, see, geometrical isomers occur as a result of restricted rotation about a carbon-carbon bond. So due to this carbon-carbon bond rotation is restricted, that is why we are that is why a molecule contains a geometrical isomers. Okay, now coming to a conformational isomer. So what is conformational isomer? Conformational isomers are the isomers that can be converted into one another by only single bond rotation. So how? There are three conformational isomers are possible. One is the eclipse, gauge, and the third one is the anti. So they have taken the butane as a example. Now you can see eclipse. Eclipse means the identical groups are all directly in line. That is called as a eclipse. So this is the eclipse isomer, the first one. The second one is the anti. So CH3 and CH3 are the anti to each other. That means 180 to each other. And the third one is the gauge. That is the 60 degree to one from another. CH3 and CH3 is the 60 degree to each other. This molecule can be interconverted by rotating around the central carbon-carbon single bond. Okay, now it's coming to an important part of this stereochemistry. This is the representation of how you can represent one molecule in a 3D manner. Let's say, if you see in any case, if you see in this kind of bold line that represents the plane of the above of the plane, and if you see in that this ordinary line that is represents the plane of the paper, and if you see the traced line or broken line, it represents below to the plane of the paper. Okay, so they have taken the ball and stick model of the 3D structure of the methane. So where you can see the two hydrogen in the plane, and the two hydrogen, one hydrogen is the below to the plane and another hydrogen is the above to the plane. The another projection is the Fisher projection. So here you can see the Fisher projection W and X is the plane, and the Y and G is the above of the plane and the below the plane. Now you can see this is the way of the Fisher projection one can represent by this way. Okay, now it is coming to the another formula of this one is the three-dimensional formula. This is the Sauhorst formula. So one can also represent a so many times people are also asked this type of question. Let's say they will give you one example and they will ask, so represent this molecule in a Sauhorst formula. So this is the Sauhorst formula. So Sauhorst formula, let's say they have taken the C2H6 where the CH3 and CH3 is the same side parallel to each other. That is why it is a eclipse conformation. And anti conformation, this is the anti to each other, 180 degree to each other. The second one. The third one is the gauge conformation. Gauge conformation is the 6 degree to each other. This is the three isomers, conformational isomers is possible. And another one is the Newman projection. They can also ask they will give you one exam molecular formula. They will ask the Newman projection of this isomers. You can draw it. Uh, so this is the three isomers is possible. One is the eclipsed isomer that is parallel to each other, and the anti-isomer where the same molecule will be anti to each other, and gauge in the 6 degree to each other. This is the Newman projection of the 3D dimensional to a molecule. Now, elements of symmetry. What kind of symmetric molecules are present in stereochemistry? Let's say one molecule. If we take one example, so this molecule contains how many symmetry of this element? So one is the plane of symmetry. So what is plane of symmetry? The plane which divides the molecule into two equal halves which are related as object and mirror image is known as the plane of symmetry. Let's say if this is the whole molecule, if we pass the plane from here, so you will end up getting two equal half of this part. Even also if you pass from this way, then also you will end up getting two equal halves of this one. So that is why you can say this molecule contains one plane of symmetry. Even if you take this kind of molecule, this example of this one, here also, although this carbon, two carbon center is the chiral center, but still the molecule contain one plane of symmetry. So that is why this molecule is also achiral. But one important point to be noted, this is the chiral molecule is always optically active. The molecule having plane of symmetry are achiral. So achiral means optically inactive. Okay, now coming to the another symmetry of this stereochemistry, that is the center of symmetry. So what is center of symmetry? So center of symmetry in a molecule is said to exist if a line is drawn from any atom or group to this point and when extended to an equal distance beyond this point and meets the identical atom or groups. So let's say this CH3 and hydrogen is the above to the plane and the hydrogen is the below to the plane. Here hydrogen is the above to the plane, CH is the below to the plane. Now if you draw a line from CH3 above to the CH3 below to the plane, so it meets the center of this molecule. So you can see that the center of symmetry is present. And also here also COO is below to the plane Here also in this center C double is the above to the plane. So if you draw a line here, it is also meets to the center of this molecule. So in that conclusion, you can say that the molecule contains a center of symmetry. So one way to present this center of symmetry is the short node is the center of symmetry is the I, and the plane of symmetry is the sigma. This is shortly saying people like the sigma. So another interesting example in the next slide I will show dimethyl ketopiperazine. This has two isomers, cis and trans, but the cis isomer has no plane of symmetry or center of symmetry. The trans form, on the other hand, has a center of symmetry. See, you can see this is the cis molecule. Why it is hydrogen? Hydrogen is in the cis to each other, and the CH3 is the cis to each other. So that is why this is not the this molecule not contain any symmetry of this molecule. Neither the symmetry or the plane of symmetry or neither the center of symmetry. But in the case of trans molecule, see this is the CH3 and the above CH3 is if we draw a line, dotted line, it meets to the center of this point. Even this hydrogen also, if we draw a line, this line from this above hydrogen to below hydrogen, it meets also center. So that means the trans isomer has a center symmetrical with respect to center of the molecule. So the trans molecule are symmetrical with respect to the center of the molecule. But no, the cis form of this piperazine, dimethyl piperazine, is not symmetrical with respect to central point. Okay, and thank you to all.